Tonight, we're going to look at the planet you think you love the most, Saturn. Golden, calm, impossibly beautiful, floating in the outer solar system like something painted rather than formed. It is the planet everyone points to first, the one children draw with crayons, the one astronomers call the jewel of the solar system. And that is exactly the problem, because everything about Saturn's appearance is a lie. Behind those perfect rings is a system of gravitational violence, atmospheric crushing pressure, planet-wide storms, and orbital debris moving at tens of thousands of miles per hour. Saturn does not look dangerous. It looks serene. And by the end of tonight, you're going to understand why that serenity is the most terrifying thing about it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. When most people think about which planet in our solar system is the most dangerous, the most violent, the most terrifying, they almost always say Jupiter. And you can understand why. Jupiter does not hide what it is. Its atmosphere is a visible war zone. Cloud bands thousands of miles wide stretch and tear across its face in opposite directions, driven by jet streams of extraordinary power. The Great Red Spot, a storm system larger than Earth that has been raging in some form for centuries, sits there in plain view like an open wound in the atmosphere. Jupiter's radiation belts are the most intense of any planet in the solar system, powerful enough to deliver a lethal dose of radiation to an unshielded human in a matter of minutes. Its magnetic field is roughly 20,000 times stronger than Earth's, stretching so far out into space that it would be visible from Earth as an object larger than the full moon if human eyes could see magnetic fields. Jupiter's gravity dominates the inner solar system, redirecting asteroids and comets, reshaping orbits, and pulling on everything within its enormous sphere of influence. Jupiter looks dangerous. Jupiter sounds dangerous when you describe it. Jupiter is dangerous. No serious person looks at a photograph of Jupiter and thinks, that seems fine. The swirling chaos in the atmosphere, the sheer mass of the thing, the radiation that would cook electronics and tissue alike. Everything about Jupiter advertises hostility. And in a strange way, that honesty works in your favor if you are trying to survive in the solar system. You look at Jupiter and you know immediately and instinctively that this is not a place you want to be. Everything about it screams threat. Its appearance matches its reality. There is no mismatch between what you see and what you get. You can prepare for Jupiter because Jupiter tells you what it is. Saturn is different. Saturn does not warn you. Saturn from any reasonable distance looks like the opposite of threat. Its color is a soft, warm gold, sometimes fading to pale yellow or honey or cream, depending on the season and the viewing angle. Its cloud bands are muted and subtle, blending together in gentle gradients rather than slashing across the planet in violent contrasts, the way Jupiter's do. There are storms on Saturn, but they tend to stay hidden below the upper haze layers, invisible for decades at a time before erupting with a violence that catches even planetary scientists off guard. The overall impression from a distance is of something smooth, composed, almost relaxed. And then, of course, there are the rings. Those extraordinary, impossibly photogenic rings sweeping out from the planet's equator in a broad, flat disk that catches the sunlight and glows with a kind of geometric perfection that seems intentional. Some of the most iconic images in all of space photography are Cassini's views of Saturn backlit by the sun, the rings glowing translucent, the planet silhouetted in gold and shadow. Saturn looks like something an artist would design. Something serene. Something inviting. If the planets were faces, Jupiter would be the one visibly clenching its jaw. Saturn would be the one smiling softly and saying nothing. And that is the deception. Because Saturn is not safe. Saturn is not calm. Saturn is not gentle. Saturn is one of the most physically extreme environments in the entire solar system. Its equatorial winds are faster than Jupiter's. Its periodic storms are among the most explosive atmospheric events ever observed on any planet. Its atmosphere has no solid surface, no floor, no bottom in any structural sense. Its rings are not decoration. They are a debris field of trillions of fragments, each one orbiting at tens of thousands of miles per hour. And its gravity, its magnetosphere, its radiation, its moons, and its orbital environment form an interconnected system of physical hostility that hides behind one of the most beautiful exteriors in all of nature. Tonight, we are going to take that exterior apart piece by piece, and we're going to start with the thing everyone notices first when they look at Saturn, the rings. Saturn's rings are the single most recognized feature of any planet in the solar system. When Galileo first observed Saturn through his small telescope in 1610, he saw something unusual on either side of the planet but could not resolve what it was. His instrument was too weak. He described Saturn as having what appeared to be ears or possibly two companion objects pressed close against it. It was not until 1655 that the Dutch astronomer Christian Huygens, using a significantly better telescope, correctly identified the feature as a flat ring surrounding the planet, detached from its surface and tilted relative to our line of sight. 20 years later, the Italian-born astronomer Giovanni Cassini discovered a prominent dark gap within the ring, dividing it into two broad sections. That gap is now called the Cassini division, and it became one of the first clues that the rings were not a single solid structure. For centuries after those early observations, the popular image of Saturn's rings remained largely the same. They looked solid. They looked stable. They looked like a permanent, elegant accessory, as though Saturn had simply been built with them. That image persisted well into the space age, even when scientists understood intellectually that the rings were made of particles. The visual impression from telescopes and early spacecraft flybys reinforced the sense of something fixed and orderly. That image is wrong. The rings are not solid. They are not a sheet. They are not a disk of material behaving as a single object. They are composed of trillions upon trillions of individual particles, each one independently orbiting Saturn under the influence of the planet's gravity. These particles are overwhelmingly water ice. Some are nearly pure, brilliantly white and reflective. Others are contaminated with traces of silicate rock, organic compounds, and dust that darken them slightly. Their sizes span an enormous range, from microscopic grains finer than powdered sugar to irregular boulders and chunks roughly the size of a small house. Most of the mass is concentrated in the particles between a centimeter and a few meters across, with the very largest objects reaching about 10 meters, and every single one of them is moving fast. This is the part most people never think about when they admire photographs of Saturn's rings. Every particle in that ring system is in orbit. It is moving. At the inner edge of the B ring, the brightest and most massive ring section, particles orbit Saturn at approximately 46,000 miles per hour. At the outer edge of the A ring, the outermost of the bright main rings, the orbital speed drops to roughly 37,000 miles per hour. These are not gentle drifts. These are velocities comparable to the fastest spacecraft humanity has ever launched. And the particles are not orbiting through empty space. They are orbiting through a crowded field of other particles, all traveling at slightly different speeds depending on their precise distance from Saturn. Inner particles move faster, outer particles move slower, and where different orbital lanes come close together, particles interact. The result is constant collision. Not dramatic, explosive collision in most cases, but an endless grinding, low-velocity contact between neighboring particles that never stops. They bump, they chip, they fracture. They sometimes stick together briefly through weak surface forces before being knocked apart again by the next encounter. Over time, large particles are worn down into smaller ones. Smaller ones are ground into dust. The dust migrates under the influence of radiation pressure and Saturn's magnetic field. Nothing in the ring system stays the same for long if you watch closely enough. The ring system, viewed at close range, is not a serene, frozen disk. It is an ongoing process of mechanical erosion. A mill of frozen debris that has been churning for as long as the rings have existed. And the energy driving this process is gravity itself. When the Cassini spacecraft arrived at Saturn in 2004 and spent the next 13 years studying the system in extraordinary detail, it revealed just how dynamic this environment truly is. The rings are alive with structure. Density waves ripple through the particle field, triggered by the gravitational influence of Saturn's moons, creating patterns of compression and expansion that propagate through the ice like sound waves through air. Narrow gaps are carved and maintained by tiny moonlets embedded within the ring material, some only a few hundred meters across, each one trailing a visible gravitational wake through the surrounding debris like the bow wave of a ship cutting through water. Clumps form and dissolve, edges sharpen and blur. Features that were visible in one Cassini orbit were gone by the next. The rings look smooth and static from Earth. From orbit, they are a dynamic, constantly shifting, violently active environment where nothing is truly at rest. Now, here is the question that should be forming in your mind. Why do the rings exist at all? Why does Saturn have this enormous field of orbiting debris instead of another moon? The answer is one of the most elegant and frightening concepts in planetary science. It is called the Roche limit. In 1849, the French mathematician Edouard Roche published a calculation that sounds simple but has profound consequences. He showed that any body held together primarily by its own gravity will be torn apart if it orbits too close to a much more massive body. The reason comes down to tidal forces, the same kind of forces that cause ocean tides on Earth, but scaled up enormously. Gravity weakens with distance. The side of a moon facing Saturn is pulled more strongly than the far side because it is closer. This difference in gravitational pull creates a stretching force across the moon, trying to pull it apart. If the moon is far enough from Saturn, its own self-gravity, the mutual attraction between all the material inside it, is strong enough to resist this stretching, the moon holds together. But if the moon drifts too close, below a critical distance, the tidal stretching force exceeds the moon's self-gravity, and the moon is pulled apart, ripped into fragments by the very gravity of the planet it orbits. That critical distance is the Roche limit. For Saturn, this boundary sits at roughly 2.5 times the planet's radius from the center, though the exact value depends on the density and internal strength of the orbiting body. An object made of loose rubble or unconsolidated ice, held together only by its own gravity, will be destroyed farther out. A solid, dense, internally strong object might survive slightly closer. But the principle is the same in every case. Inside the Roche limit, Saturn's tidal forces overpower self-gravity. Anything that enters that zone and lacks sufficient internal material strength to resist the stretching gets pulled apart. Not explosively, not all at once. The tidal forces work patiently. They stretch the object along the line connecting it to Saturn, elongating it, pulling it into a shape it cannot sustain. Fractures open, fragments separate, the pieces drift into independent orbits, and over time, those fragments are ground down further by collisions with other debris already in the ring plane. Saturn's main ring system, the broad, bright structure visible through any decent telescope, sits almost entirely within this boundary. That is not a coincidence. The rings exist inside the Roche limit because they cannot do anything else. Inside that invisible line, particles of ice and rock can orbit Saturn freely, but they cannot accumulate into a larger body. Any clump that begins to form, any collection of particles that starts to pull itself together through its own gravity, gets stretched and disrupted by Saturn's tidal forces before it can finish the job. The material is trapped in a state of permanent fragmentation. It orbits, it collides, it grinds, but it can never become a moon. What this means is that the rings are not a feature that Saturn simply has. They are a consequence of gravitational violence. The ring system marks a kill zone around Saturn. Anything that drifts inside the Roche limit and is not strong enough to hold itself together gets destroyed. What you are looking at when you see Saturn's rings is not decoration. It is the accumulated wreckage of everything that came too close. The debris of moons that wandered inward. The shattered remains of comets captured by Saturn's gravity. The remnants of collisions between objects already orbiting inside the danger zone. Every particle in the ring system is a fragment of something that was destroyed by Saturn's gravity. The rings are beautiful because of their scale and their geometry, but the process that created them is destruction, and the process that maintains them is the same. And those rings are not finished. They are not in a stable, permanent state. They are actively being consumed by the planet they orbit. During the final phase of the Cassini mission, NASA executed what it called the grand finale. 22 daring orbits that threaded the spacecraft through the gap between Saturn's innermost ring and the planet's upper cloud layer. That gap is approximately 1,200 miles wide, a razor-thin corridor in orbital terms. No spacecraft had ever flown through this region. The risks were significant. The potential for collision with stray ring material was real, and the engineering precision required was extraordinary. But the grand finale delivered discoveries that fundamentally changed our understanding of Saturn's ring system. Cassini's instruments detected vast quantities of material falling from the rings into Saturn's atmosphere, not in rare, sporadic events, but continuously, without pause, every second of every day. a steady rain of water ice, silicate dust, and organic compounds pulled from the rings and drawn into the planet through two main pathways. The first is ring rain in the traditional sense, a process in which ring particles become electrically charged by ultraviolet light from the sun or by the impacts of micrometeoroids striking the ring surface. Once charged, these tiny particles get caught by Saturn's magnetic field lines, which act like invisible rails connecting the rings to the planet's atmosphere. The charged grains slide along these magnetic field lines and plunge into Saturn's upper atmosphere at mid to high latitudes, neutralizing ions in the ionosphere and altering the planet's atmospheric chemistry in measurable ways. This process was first hypothesized in the early 1980s, based on strange dark bands observed in Saturn's upper atmosphere by Voyager 1 and Voyager 2, bands that seem to correspond geographically to locations where ring-connected magnetic field lines intersected the planet. Cassini confirmed the process directly. The second pathway is direct equatorial infall, where uncharged ring material, mostly from the innermost ring edges, simply falls into the atmosphere under gravity without being guided by the magnetic field. This component turned out to be far larger than anyone expected. During the grand finale orbits, Cassini flew directly through the region where this infall occurs and measured the density and composition of the falling material. Together, these two processes drain material from the ring system at a rate that stunned researchers. The numbers vary depending on the study and the measurement method, but the combined loss rate is estimated at somewhere between 400 and roughly 10,000 kilograms per second. At the ring rain rate measured by ground-based observations, the rings are losing enough water to fill an Olympic-sized swimming pool approximately every 30 minutes. Factor in the equatorial infall measured during the grand finale, and the total loss rate climbs even higher. At these rates, the entire ring system could be gone within 100 to 300 million years. Some estimates, factoring in the equatorial loss measured by Cassini, place the timeline at less than 100 million years. That sounds like an impossibly distant future, and by human standards it is, but Saturn is approximately 4.5 billion years old. The solar system is approximately the same age. If the rings vanish within 300 million years, they will have lasted for less than 7% of Saturn's total history. In cosmic terms, the rings are not permanent. They are a brief episode, a passing phase, and we happen to exist during the narrow window when they are visible. This raises one of the most actively debated questions in planetary science today. When did the rings form? For most of the 20th century, the default assumption was that Saturn's rings were primordial. They formed alongside the planet roughly 4.5 billion years ago from material in the early solar nebula that could not coalesce into a moon because it lay within the Roche limit. This was a clean, simple explanation that fit with the general picture of planetary formation. But Cassini's measurements shattered that assumption. During the grand finale, precise tracking of the spacecraft's trajectory as it passed close to the rings allowed scientists to measure the total mass of the ring system with extraordinary accuracy. The result, published in 2019, was a surprise. The rings contain only about 40% the mass of Mimas, one of Saturn's smaller moons, itself only about 246 miles across. That is remarkably little material for a structure spanning roughly 175,000 miles. Then came the contamination measurement. In 2023, a study led by researcher Sascha Kempf and colleagues measured the rate at which micrometeoroid dust from interplanetary space falls onto Saturn's rings. Over billions of years, this constant dusting should contaminate the ring ice, mixing in dark, non-icy material and gradually dimming the ring's reflectivity. But Saturn's rings are still strikingly bright and clean, far brighter than they should be if they had been accumulating interplanetary dust for 4.5 billion years. The analysis concluded that the ring's exposure age, the time they've been sitting in space collecting dust, is no more than a few 100 million years. This places their formation somewhere around the era when dinosaurs walked the Earth, or possibly even more recently. If the rings are young, something must have created them relatively recently. One leading hypothesis, supported by a 2023 study published in the Astrophysical Journal, proposes that two moons within the Saturn system collided, and the resulting debris spread into orbit inside the Roche limit, forming the ring system we see today. A separate 2026 study from the SETI Institute and collaborators suggested that the origins of Titan and Hyperion themselves may trace back to a dramatic merger between two ancient moons, an event that could also have generated ring-forming debris. But the young ring hypothesis is not settled science. A 2026 study by Gregorio Riccherchi and Aurelian Crida, published in the journal Icarus, argued that the contamination clock used to date the rings relies on assumptions that may not hold. If infalling micrometeoroids vaporize on impact rather than sticking to ring particles, the vaporized material could be swept away by Saturn's magnetosphere rather than accumulating as visible contamination. In that case, the ring's current brightness and cleanliness would not reliably indicate a young age. A similar argument appeared in a 2025 study by Ryuki Hyodo and colleagues, who showed that micrometeoroid impacts can produce fine vapor and grain byproducts that interact with Saturn's magnetic field and are removed from the ring system entirely. If this removal process is efficient, the rings could be old and still look clean. The debate is genuine and ongoing. It involves some of the most sophisticated modeling in planetary science, and different groups working with different assumptions about ring physics arrive at meaningfully different conclusions. What is not in dispute is the present state of the rings. They are losing mass. They are dynamic. They are eroding. Whether they are young and dying quickly, or ancient and eroding slowly, they are not the stable, timeless structure people imagine when they see Saturn in a photograph. The structure of the ring system itself reinforces just how dynamic it is. Saturn does not have one ring. It has a complex system of distinct regions, each with different densities, compositions, and behaviors. The D ring is the innermost, a faint and wispy band sitting closest to the planet's cloud tops. Outside, it lies the C ring, thin and partly translucent, sometimes called the crepe ring for its delicate appearance. Then comes the B ring, the densest and most massive section, containing the bulk of the ring system's material. This is the ring that dominates images of Saturn, bright and opaque, packed so densely with particles that light from behind it is almost completely blocked. Beyond the B ring, separated by the dark Cassini division, a gap roughly 3,000 miles wide that is maintained by an orbital resonance with Saturn's moon Mimas, sits the A ring, another broad, bright band. Past the A ring is the thin, twisted F ring, confined by the gravitational influence of two small shepherd moons, Prometheus and Pandora, whose competing pulls give the F ring a kinked, braided appearance that visibly changes over weeks and months. And far beyond all of these is the enormous, diffuse E ring, a vast band of microscopic ice particles that extends outward for hundreds of thousands of miles, fed almost entirely by the water vapor geysers erupting from Saturn's tiny moon Enceladus. Each of these regions tells a different piece of the story, and none of them are static. The gaps are maintained by gravitational resonances with moons. A particle orbiting within the Cassini division, for instance, completes exactly 2 orbits for every single orbit of the moon, Mimas. This 2-to-1 resonance gradually nudges particles out of the gap over time, keeping it relatively clear. Similar resonances carve narrower gaps throughout the ring system, each one a gravitational fingerprint left by a specific moon at a specific distance. The density structures within the rings are shaped by waves, wakes, and perturbations from embedded moonlets. Spiral density waves, resembling the spiral arms of galaxies in miniature, wind through the ring material for hundreds of miles, compressing and rarefying the particle density in patterns that can be used to measure the mass and properties of the rings themselves. Bending waves tilt sections of the ring material slightly out of the plane, creating corrugations that propagate outward from the source of the perturbation. The B ring contains radial features called spokes, dark or bright markings that appear and vanish over the course of hours, likely created by electrostatic interactions between ring particles and Saturn's magnetic field. When Voyager first photographed them in 1980 and 1981, they were among the most puzzling features ever observed in a planetary ring system. Spokes should not exist. The differential rotation of the ring, where inner particles orbit faster than outer ones, should shear any radial feature apart within minutes. Yet spokes persist for hours before fading, suggesting they are continuously generated and maintained by electromagnetic forces rather than orbital mechanics alone. The edges of certain rings show vertical distortions where material has been kicked out of the flat ring plane by gravitational interactions, creating wall-like structures that cast long shadows when the sun sits at a low angle relative to the ring plane. During Saturn's equinox in 2009, when sunlight struck the rings nearly edge-on, Cassini photographed vertical features at the outer edge of the B ring that rise roughly 2.5 kilometers above the ring plane. This is remarkable because the main rings, despite spanning roughly 175,000 miles in width, are astonishingly thin. The B ring in most places is only about 30 feet thick. That ratio of width to thickness is almost impossible to visualize. If you scaled the B ring down so that its width matched the length of a football field, its thickness would be less than the width of a human hair. It is one of the flattest large-scale structures known in nature. Yet even within that impossibly thin sheet, the physics is violent, dynamic, and continuously evolving. The ring system is not an ornament. It is not a frozen relic. It is a debris field in motion, shaped by gravity, eroded by magnetic forces, fed by collisions and moon eruptions, and slowly draining into the planet that holds it captive. It is one of the most beautiful things in the solar system, and every part of that beauty is the product of forces that would destroy anything human-made in an instant. And the rings, as extreme as they are only the outermost layer of Saturn's hostility. They are the frame around a portrait that gets far darker the closer you look. Because beneath those rings, past the thin veil of golden cloud that gives Saturn its warm and inviting color, is something far more extreme. An atmosphere that does not end. A sky that becomes a sea, that becomes a furnace, that becomes a pressure so immense it crushes hydrogen itself into a liquid metal. There is no surface. There is no boundary. There is only a gradient of deepening violence that gives no warning and offers no flaw. And that is where we are going next. On Earth, the atmosphere has a bottom. You can stand on it. The air sits on top of rock, and the rock holds you up. And below the rock is more rock. And below that is metal. And eventually, roughly 4,000 miles beneath your feet, you reach the center of the planet. There is a structure. There are layers. There are boundaries you can name and point to. The ground is the ground. You know where you are. Saturn does not work this way. Saturn is a gas giant. That term gets used so casually in popular science that it is easy to forget what it actually means. It does not mean a rocky planet with a thick atmosphere. It does not mean a world with a surface hidden somewhere beneath the clouds, waiting to be discovered if you could only descend far enough. It means the planet is made almost entirely of gas. Hydrogen and helium, top to bottom, through and through. Approximately 96% hydrogen and roughly 3% helium by volume, with traces of methane, ammonia, water vapor, and other compounds that form the colourful cloud layers you see in photographs. There is no crust. There is no mantle. There is no continental plate, no ocean floor, no bedrock, no ground. If you fell into Saturn's atmosphere from above, you would not eventually hit something solid. You would simply keep falling, and as you fell, the gas around you would get denser and hotter, and the pressure would increase, and at some point the gas would thicken into something more like a liquid, and then into something stranger still. And at no point during this entire descent would you ever encounter a surface. There is no moment where you stop falling because you have arrived. There is no landing. You stop falling only when the density of the fluid around you eventually matches the density of whatever is falling. And at that point, you are not standing on anything. You are not resting on anything. You are suspended, neutrally buoyant, inside a planet that has no floor. And the temperature and pressure at that depth would have long since destroyed anything made of any material known to human engineering. This fact changes everything about how you think about Saturn's danger. A rocky planet can be hostile on its surface. It can have volcanoes, toxic atmospheres, extreme temperatures. But at least you can point to the surface and say, there, that is the boundary. Saturn offers no such clarity. Its hostility is not at a location. It is a gradient. It gets worse the deeper you go. Smoothly, continuously, without any line you can draw and call the edge. And it starts getting hostile much sooner than most people realize. The upper atmosphere of Saturn, the thin visible layer that gives the planet its golden appearance, is already one of the most violent atmospheric environments in the solar system. Saturn's equatorial winds reach speeds of approximately 1,100 miles per hour. To put that in perspective, the most powerful hurricane winds ever measured on Earth top out at roughly 220 miles per hour. Saturn's equatorial jet stream moves 5 times faster than that. These are not gusts or peak readings from brief, exceptional events. They are sustained, permanent flows of atmospheric gas that have been measured consistently by every spacecraft that has visited the system. They are driven by the planet's rapid rotation, its enormous internal heat output, and atmospheric dynamics that planetary scientists still do not fully understand. The winds blow in alternating east-west bands that wrap the entire planet, creating the subtle striped pattern visible in enhanced color images. Eastward jets alternate with westward jets, each one spanning thousands of miles of latitude. The equatorial jet is by far the broadest and fastest, but even the smaller jets at higher latitudes move at hundreds of miles per hour, fast enough that any physical object caught in the shear between two opposing jets would be subjected to forces that would rip apart structures far stronger than anything we have ever sent into space. Saturn rotates once approximately every 10 hours and 33 minutes. For a planet with an equatorial diameter of roughly 74,800 miles, that rotation speed is extraordinary. Points on Saturn's equator are moving at roughly 22,000 miles per hour, just from the rotation of the planet itself. This rapid spin stretches the atmosphere into the bands visible in telescopic images, creates powerful jet streams at the boundaries between those bands, and drives a circulation pattern that reaches deep into the planet's interior. The winds are not a surface phenomenon. Research from the Cassini Grand Finale gravity measurements, published in 2019, showed that Saturn's atmospheric winds extend without significant decay to a depth of at least 6,000 miles below the visible cloud tops. That is deeper than the radius of Earth. The winds you see in photographs of Saturn are not a thin weather layer sitting on top of a calm interior. They are the visible face of a circulation system that reaches down through a significant fraction of the planet's volume. And within that atmosphere, Saturn produces features that are unlike anything else in the solar system. At Saturn's North Pole sits a structure that has puzzled planetary scientists for over 4 decades. It is a hexagonal jet stream, a 6-sided pattern of atmospheric flow, roughly 20,000 miles across, with winds of approximately 200 miles per hour defining its edges, and a massive rotating cyclone sitting at its exact center. Each side of the hexagon stretches for roughly 10,000 miles, comparable to the distance from London to Sydney. The entire structure is large enough that more than 2 Earths could fit side by side across it. And it has been there, in recognizably the same shape and the same location, for at least as long as we have been able to observe it. The hexagon was first glimpsed by Voyager 1 during its flyby in 1980. At the time, the images were grainy and incomplete, and the feature was treated as a curiosity. It was not until the Cassini spacecraft arrived and began systematic observations starting in 2004 that the hexagon was studied in detail over multiple Saturn seasons. What Cassini revealed was remarkable. The hexagon is not a temporary storm. It is not a transient feature that comes and goes. It is a persistent, stable, geometrically precise atmospheric structure that has maintained its shape through decades of observation and through seasonal changes that dramatically alter the lighting and temperature conditions at Saturn's North Pole. This should not be possible. Atmospheres are chaotic. They produce turbulence, vortices, irregular cloud formations. They do not, as a rule, produce perfect geometric shapes and then hold them fixed for 40 years. The leading explanation for the hexagon involves what are called Rossby waves, large-scale atmospheric waves generated by the rotation of the planet interacting with latitude-dependent variations in wind speed. In fluid dynamics experiments on Earth, researchers have successfully reproduced hexagonal patterns by spinning fluid at specific rates and creating differential flow between inner and outer regions. The hexagon on Saturn appears to be a standing wave, a stable pattern that emerges naturally from the interaction of jet stream speeds at different latitudes, locked in place by the planet's rotation and its deep atmospheric circulation. But the explanation, even if correct in its broad outlines, does not diminish the strangeness. The hexagon is a storm system larger than Earth. Its central cyclone has wind speeds exceeding 300 miles per hour. Inside the hexagon's boundaries, smaller vortices rotate in both directions, some clockwise, some counterclockwise, some the size of major hurricanes on Earth, and the whole structure sits at Saturn's north pole, like a geometric seal stamped on the top of the planet, a reminder that the physics happening inside Saturn's atmosphere operates on scales and with a precision that our experience with Earth's weather does not prepare us for. Saturn's south pole has a different but equally dramatic feature. A massive cyclone, roughly the size of Earth, sitting directly over the pole with wind speeds exceeding 300 miles per hour, and an eye structure visible in Cassini images. A distinct, well-defined, hurricane-like eye punching down into the deeper atmosphere, surrounded by towering eyewall clouds rising 20 to 45 miles above the surrounding cloud deck. It is one of the only clear cyclone eye structures ever observed on any planet other than Earth. And unlike any hurricane on Earth, it is permanent. It does not form and dissipate the way terrestrial hurricanes do over days or weeks. It sits there, endlessly, fixed over the south pole of the planet, spinning continuously at a scale and duration that has no analogue in our experience of weather. These polar features are permanent. But Saturn also produces storms that are not permanent, storms that erupt from the deep atmosphere with a violence that temporarily changes the appearance of the entire planet. They are called great white spots, and they are among the most powerful atmospheric events ever observed anywhere in the solar system. Great white spots have been recorded 6 times since 1876. They appear roughly once every Saturn year, approximately every 29.5 Earth years. The observed storms erupted in 1876, 1903, 1933, 1960, 1990, and 2010. The most recent event, the 2010 Great White Spot, was the first to occur while a spacecraft was in orbit around Saturn, and the detail captured by Cassini transformed our understanding of what these storms actually are. The 2010 storm erupted on December 5th of that year in Saturn's northern hemisphere, near 37 degrees latitude. It began as a bright white spot, a region where material was being thrust upward from deep in the atmosphere, punching through the upper cloud deck and scattering sunlight with unusual brightness. Within 3 weeks, the storm head had grown to a width of more than 6,000 miles, roughly comparable to the diameter of Earth. Its cloud tops rose 40 to 50 kilometers above the surrounding undisturbed atmosphere. A turbulent tail streamed eastward from the storm head, stretching around the planet until, within about 2 months, the disturbance had wrapped the entire globe in a band of churning, disrupted atmosphere spanning from roughly 25 to 48 degrees north latitude. The energies involved were staggering. Cassini's radio instruments detected lightning at a rate of more than 10 flashes per second, an order of magnitude greater than any previous Saturnian storm, and thousands of times the flash rate of even the most active thunderstorms on Earth. Saturn's lightning discharges are believed to be individually far more powerful than terrestrial lightning, carrying thousands of times more energy per flash, given the greater atmospheric depth and the enormous convective energy available in Saturn's deep weather layer. The storm produced a massive temperature spike in Saturn's stratosphere. heating the upper atmosphere by approximately 83 degrees Celsius, or 150 degrees Fahrenheit, above normal levels. This was the largest temperature change ever recorded on the ringed planet. It released enormous quantities of ethylene gas, a compound not normally abundant in Saturn's atmosphere, in quantities so large that researchers were initially unsure of the chemical pathway producing it. And it drove convective plumes that dredged water ice upward from an estimated 200 kilometers below the visible cloud deck, hauling material from deep inside Saturn's weather layer and throwing it into the upper atmosphere, where it became visible as the bright white clouds that give the storm its name. 200 kilometers. That is deeper than the entire thickness of Earth's atmosphere from sea level to the edge of space. The great white spot reaches down into Saturn and digs material from a depth that, on Earth, would correspond to somewhere below the floor of the ocean. The origin of these storms is believed to lie in Saturn's unusual thermal structure. As Saturn's upper atmosphere cools seasonally, the heavier water vapor in the deeper atmosphere eventually becomes denser than the hydrogen and helium above it. For decades, this denser layer suppresses convection, sitting quietly below the visible clouds while energy builds beneath it. But eventually, the instability becomes too great. The dense layer breaks, and when it breaks, it does not produce a small, localized thunderstorm. It produces a planetary-scale eruption that tears open the atmosphere across tens of thousands of miles, releases decades of stored energy in a matter of weeks, and wraps the entire planet in turbulent cloud for months. This is one of the reasons Saturn looks so calm most of the time. The calm is not an absence of energy, it is stored energy, accumulating silently in the deep atmosphere, held down by the density structure of the atmospheric layers, waiting for the moment when the balance tips and the atmosphere tears itself open. Saturn's serenity, in this sense, is not peace, it is pressure. And when that pressure releases, the result is one of the most violent atmospheric events in the known solar system. The source of all this atmospheric violence is not the Sun. Saturn orbits roughly 9.5 times farther from the Sun than Earth does. At that distance, it receives only about 1% of the solar energy per unit area that Earth receives. If Saturn's atmosphere were driven only by solar heating, it should be a quiet, sluggish, featureless world. But Saturn is anything but quiet. It radiates approximately 2 1/3 times more energy than it absorbs from sunlight. The planet is generating enormous amounts of heat internally, and that heat drives everything. The winds, the jet streams, the hexagon, the great white spots, the deep, convective plumes. All of it is powered primarily from below, not from above. The source of this internal heat is one of the most fascinating processes in planetary science. It is called helium rain. Deep inside Saturn, at pressures measured in millions of bars and temperatures of thousands of degrees, the hydrogen and helium that make up the bulk of the planet exist in a state called liquid metallic hydrogen. Under these extreme conditions, helium becomes immiscible in the metallic hydrogen. It separates out, forming droplets, the way oil separates from water when you stop stirring. These helium droplets are denser than the surrounding hydrogen, and they sink. They rain downward through the interior of the planet, falling slowly through thousands of miles of compressed fluid, descending toward the center under Saturn's relentless gravity. As they fall, they convert gravitational potential energy into heat through friction with the surrounding material. That heat is then carried back upward through the planet by convection and eventually radiated into space from the upper atmosphere. Saturn is raining inside itself. The rain is made of helium, and the friction of that helium rain falling through thousands of miles of metallic hydrogen is what has kept Saturn's atmosphere violently active for 4.5 billion years. Without helium rain, Saturn would have cooled long ago. Its atmosphere would have settled into something closer to equilibrium. The winds might have died down, the storms might have stopped, but helium rain feeds the engine, and the engine keeps running, and the storms keep erupting, and the winds keep howling at 5 times hurricane force, and none of this shows on the planet's calm, golden face. Now, imagine descending through this atmosphere from the cloud tops downward, and pay attention to what happens at each stage, because the progression is relentless. You begin at the top of the visible atmosphere, in the thin layer of ammonia ice clouds that give Saturn its golden color. The temperature here is approximately minus 180 degrees Celsius, roughly minus 290 degrees Fahrenheit. The pressure is about 1 bar, roughly the same as sea level on Earth. If you could somehow float here, suspended in the hydrogen atmosphere, the conditions would be brutally cold, but the pressure would feel familiar. You would see hazy cloud decks stretching in every direction, tinted gold and cream by the ammonia crystals. Saturn's gravity at the cloud tops is approximately 1.06 times Earth's gravity. You would weigh roughly 6% more than you do at home. Not enough to notice. But you are not going to stay at the cloud tops. You are going down. As you descend, the pressure increases steadily. Within the first 50 kilometers below the ammonia clouds, you pass through a layer of ammonium hydrosulfide clouds at pressures of roughly 2 to 5 bars. The temperature has already climbed above minus 100 degrees Celsius. Keep going. Deeper still, roughly 100 to 200 kilometers below the visible surface, you reach the water cloud layer. Pressures here are between 10 and 20 bars, 10 to 20 times the atmospheric pressure at Earth's sea level. The temperature has risen to approximately room temperature, around 27 degrees Celsius or 80 degrees Fahrenheit. Paradoxically comfortable if you could somehow ignore the crushing pressure and the fact that you are floating inside a planet with nowhere to go. This is the layer from which the great white spot storms dredge their material upward. It is also roughly the deepest layer where distinct cloud formations exist, where material condenses and forms visible structures. Below this point, there are no more clouds. There are no more distinct layers. There is only hydrogen gas, getting denser, getting hotter, getting heavier. The light from the sun above has long since been absorbed by the layers overhead. It is completely dark, and it keeps getting thicker, and it keeps getting thicker. The pressure climbs, 100 bars, 500 bars, 1,000 bars. At roughly 1,000 bars, approximately 1,000 kilometers below the cloud tops, the temperature has reached about 730 degrees Celsius, roughly 1,350 degrees Fahrenheit, and the hydrogen has become so compressed that the distinction between gas and liquid begins to lose meaning. There is no boiling point at this pressure. There is no surface of a liquid forming below you. The hydrogen simply becomes denser and denser, transitioning smoothly from a state that behaves like a thick gas to a state that behaves like a hot, thin liquid without ever crossing a sharp boundary. This is called a supercritical transition. and it is one of the most disorienting physical realities of Saturn's interior. It means there is no moment when you cross from atmosphere into ocean. There is no splash. There is no surface contact. There is no dramatic threshold where everything changes. The medium around you just gets gradually heavier and thicker and hotter, and you sink deeper, and the pressure keeps climbing, and the transition from sky to sea happens around you so smoothly that if you were somehow still alive and still conscious, you would not even be able to identify the moment it occurred. At 10,000 bars, roughly 5,000 kilometers below the cloud tops, the temperature exceeds 2,000 degrees Celsius. The hydrogen around you is now unambiguously a liquid, a hot, dense, compressed fluid with no surface above it and no floor below it. Nothing human-built would survive here. The pressure is already 10,000 times the atmospheric pressure at Earth's sea level, more than 9 times the pressure at the bottom of the Mariana Trench, the deepest point in Earth's oceans. And you are not even close to the center of the planet. Continue deeper. The pressure reaches 100,000 bars, then 1 million bars, then 2 million bars. At pressures of a few megabars, roughly halfway between the cloud tops and Saturn's center, a profound transformation occurs. The hydrogen, under this nearly unimaginable degree of compression, changes state once more. The molecules of hydrogen are forced so close together that their electrons are stripped free from individual atoms and begin to move freely through the fluid, the way electrons move through a metal. The hydrogen becomes electrically conductive. It becomes, in effect, a liquid metal. This state is called liquid metallic hydrogen, and it does not exist naturally anywhere on Earth's surface. It cannot be produced in any laboratory for more than tiny fractions of a second under extreme experimental conditions. But inside Saturn, it makes up a vast fraction of the planet's volume. This layer of metallic hydrogen is where Saturn's magnetic field is generated. The flowing, electrically conductive fluid, churned by convection and shaped by the planet's rapid rotation, acts as a planetary dynamo, producing a magnetic field that extends millions of miles into space. It is also the layer into which helium rain falls, sinking through the metallic hydrogen toward the center and releasing the frictional heat that powers Saturn's atmospheric violence from below. And below even this metallic hydrogen layer, at the very center of Saturn, lies the core. Or rather, what models and measurements suggest should be a core. Cassini's grand finale gravity data and ring seismology observations, which use the pattern of waves in Saturn's sea ring to probe the planet's internal density structure, the way seismologists use earthquake waves to probe Earth's interior. Both indicate that Saturn has a central concentration of heavy elements: rock, ice, and metals, weighing somewhere between 12 and 20 Earth masses. But this core is not compact. It is not a distinct ball of rock sitting at the center of the planet with a clear boundary separating it from the hydrogen above. Instead, it is diffuse, fuzzy, blurred. The heavy elements gradually thin out as you move outward, mixing with the surrounding metallic hydrogen in a broad transitional zone that may extend outward to roughly half of Saturn's total radius. There is no sharp core boundary. Just as there is no sharp surface at the top, there is no sharp center at the bottom. Saturn is a planet of gradients, of smooth and continuous transitions between states, of boundaries that dissolve into each other when you try to define them precisely. And at the very center of this diffuse core, the temperature is estimated at roughly 10,000 Kelvin, approximately 17,500 degrees Fahrenheit. That is nearly twice the temperature of the visible surface of the Sun. The center of Saturn, a planet that looks cool and golden from the outside, is hotter than the surface of the star it orbits. This is what sits behind that golden, smiling exterior, an atmosphere that begins with ammonia ice and ends with a liquid metal. Winds that outrun Earth's fastest jets. A hexagonal storm larger than a planet. Periodic eruptions that wrap the entire globe in chaos. A rain of helium falling through thousands of miles of metallic fluid. And a core hotter than the surface of the star that lights it. None of this is visible from the outside. None of it shows on Saturn's calm, golden face. Saturn does not merely lack a surface. It lacks a boundary of any kind. No surface, no shore, no wall, no edge between one zone and another. Just a smooth, continuous slide from cold, thin gas at the top to hot liquid metal at the bottom, and every stage of that slide is worse than the one above it. The pressure climbs without ceiling. The temperature climbs without limit. The density climbs without relief. There is no point during the descent where anything stabilizes. Where the conditions plateau, where you can say, at least it will not get worse than this. It always gets worse, and there is nowhere to stop. A planet that has no surface cannot be landed on, cannot be stood upon, cannot be mapped in the way a rocky world can be mapped. There is no here on Saturn. There is only deeper. And every direction you call down leads only to more heat, more pressure, more density, and eventually to a core so blurred into its surroundings that even the concept of center becomes approximate. Saturn is not a place, it is a process, a continuous compression of matter from the cold vacuum of space at the top to a metallic furnace at the bottom, with no interruption and no relief at any point along the way. And yet, we have not talked about the space around Saturn, because the atmosphere, as extreme as it is, occupies only the volume of the planet itself. The Saturn system extends much farther than that. Hundreds of thousands of miles of orbital space, filled with hundreds of moons, active debris fields, radiation belts, and electromagnetic forces that connect the rings to the planet, and the moons to the rings in a web of physical interactions that makes the entire system behave not like a planet with accessories, but like a single interconnected machine. A machine whose individual components feed energy and material to each other across distances of hundreds of thousands of miles. A machine that is, in every measurable way, hostile to anything that enters it from outside. That machine is what we are going to examine next. So far, we have looked at two layers of Saturn's hostility. The rings, which are not decoration but a high-velocity debris field inside the Roche limit. And the atmosphere, which is not a thin shell around a solid planet but a bottomless well of increasing pressure, temperature, and density that transitions smoothly from gas to liquid to metallic fluid without ever offering a surface. Both of these are dangerous. Both of them would destroy anything we sent into them. But both of them are contained within Saturn itself, within the volume of the planet and its immediate ring system. The danger of Saturn does not stop there. It extends outward, far beyond the rings, far beyond the visible disk of the planet, into a volume of space so large and so interconnected that planetary scientists no longer think of Saturn as a planet with moons and rings attached to it. They think of it as a system. A single, integrated, physically coupled system in which the planet, the rings, the magnetosphere, the radiation belts, and its enormous population of moons all interact with each other, exchanging material and energy and electromagnetic force across distances of hundreds of thousands of miles. And that system, taken as a whole, is one of the most complex and hostile environments in the solar system. Let us start with what it takes to approach Saturn. Saturn is enormous. Its equatorial diameter is roughly 74,800 miles, more than 9 times the diameter of Earth. Its mass is approximately 95 times Earth's mass. That mass means gravity, and that gravity dominates a volume of space that extends millions of miles in every direction. Any spacecraft approaching Saturn must contend with that gravity. It must manage its velocity with extreme precision to avoid either being flung away on a hyperbolic trajectory or being pulled in too fast and too deep. Entering orbit around Saturn requires a carefully timed engine burn to reduce speed at exactly the right moment, trading kinetic energy for a stable orbit. Too little braking and the spacecraft sails past. Too much and it drops into a lower, faster orbit that may intersect the ring plane, which, as we have already established, is not a place you want to be moving through at orbital speeds. Cassini executed this maneuver in July of 2004, firing its main engine for roughly 96 minutes to slow itself enough to be captured by Saturn's gravity. During that engine burn, the spacecraft flew through the gap between the F ring and the G ring, a region of relatively sparse material that had been carefully selected to minimize the risk of collision with ring particles. Even so, mission controllers oriented the spacecraft with its high-gain antenna pointed forward, using the 4-meter dish as a makeshift shield against any stray debris that might be drifting through the gap. A single grain of ice, striking the spacecraft at orbital velocity during the burn, could have damaged critical systems and ended the mission before it began. The insertion burn was one of the most critical moments of the entire 13-year mission. A failure at that point, after nearly 7 years of interplanetary travel across 2 billion miles, would have meant flying past Saturn forever with no way to return. Everything depended on that one engine burn succeeding in a region of space where stray ring particles could appear without warning. Once in orbit, a spacecraft must continuously manage its trajectory through a gravitational environment shaped not only by Saturn itself, but by dozens of large and mid-sized moons, each one exerting its own gravitational pull. The orbital dynamics of the Saturn system are extraordinarily complex. Moons perturb each other's orbits. Resonances between moons create zones of stability and instability. Ring material interacts gravitationally with embedded moonlets and with shepherd moons at the ring edges. Navigating through this environment for 13 years required constant trajectory updates, calculated weeks or months in advance by teams on Earth, and transmitted across roughly 1 billion miles of space at light speed, arriving with a delay of roughly 70 to 90 minutes, depending on Saturn's distance from Earth at the time. Titan, Saturn's largest moon, has enough mass to significantly alter a spacecraft's orbit during a close flyby. Cassini used more than 100 targeted flybys of Titan over the course of its mission, using Titan's gravity to reshape its orbit and reach different parts of the Saturn system without burning large amounts of fuel. Each flyby was a precisely calculated gravitational dance, approaching Titan at exactly the right angle and speed to produce the desired change in trajectory. An error of even a few miles in the flyby altitude could result in an orbit change that took weeks or months to correct. And throughout all of this, the spacecraft must operate within Saturn's magnetosphere. Saturn's magnetosphere is the region of space dominated by the planet's magnetic field. Saturn generates this field deep inside its interior, In the layer of liquid metallic hydrogen, where convective motion of electrically conducting fluid creates a dynamo, much the same way Earth's liquid iron outer core generates our planet's magnetic field. But Saturn's magnetic dipole moment, the overall strength of its magnetic influence on the surrounding space, is roughly 580 times greater than Earth's. The magnetosphere it creates extends outward from the planet to roughly 20 Saturn radii on the side facing the Sun, approximately 1.2 million kilometers, and stretches much farther in the opposite direction, drawn out into a long magnetotail by the pressure of the solar wind. Inside this magnetosphere, charged particles, electrons and protons and heavier ions are trapped and accelerated by the magnetic field, forming radiation belts similar in structure to Earth's Van Allen belts, but vastly larger. These radiation belts are less intense than Jupiter's, which are the most powerful in the solar system by a significant margin. But they are still energetic enough to pose risks to spacecraft electronics over long-duration missions, and they would be dangerous to any unshielded biological life that remained in them for extended periods. Cassini's instruments measured the particle populations within these belts throughout the mission, and the data revealed a complex, dynamic environment shaped not just by Saturn's magnetic field, but by the interactions between that field and the material being constantly fed into the magnetosphere by Saturn's moons and rings. And there is something unusual about Saturn's magnetic field that puzzled scientists for decades and still is not fully understood. Unlike every other planet with a magnetic field, Saturn's magnetic axis is aligned almost perfectly with its rotational axis, offset by no more than roughly 0.06 degrees. This is strange because dynamo theory, the branch of physics that explains how planets generate magnetic fields through the convective motion of electrically conducting fluid in their interiors, generally requires some misalignment, some tilt between the magnetic and rotational axes to function. The tilt is what creates the asymmetry that allows convection to generate a sustained field. Earth's magnetic axis is tilted about 11 degrees from its spin axis. Jupiter's is tilted by roughly 10 degrees. Saturn's near-perfect alignment, measured with extraordinary precision during Cassini's final orbits, should, according to the standard theory, not be able to sustain a dynamo at all. And yet Saturn clearly has a magnetic field. Something about Saturn's interior structure is producing this anomalous symmetry. The leading hypothesis involves a stably stratified layer of conducting fluid, sitting between the deep dynamo region where the metallic hydrogen churns and the outer atmosphere that acts as a filter. This layer smooths out any tilt in the underlying field before it reaches the surface, producing the unnaturally perfect alignment observed from outside. Saturn's magnetic field, like so much else about the planet, is hiding its true internal structure behind a mask of apparent simplicity. This magnetic field also created one of the longest running mysteries in Saturn science, one that was only resolved in 2026. For decades, scientists have been trying to determine how fast Saturn rotates, its true internal rotation period, the length of one Saturn day. On a rocky planet, this is straightforward. You watch a surface feature and time how long it takes to rotate back to the same position. But Saturn has no surface. Its visible cloud features move at different speeds, at different latitudes because of the powerful winds. So tracking clouds does not give you the rotation of the planet itself. The alternative is to use the magnetic field. A planet's magnetic field is generated in its deep interior and rotates with it. By measuring periodic signals in the magnetic field, particularly radio emissions that are modulated by the field's rotation, you can infer the rotation rate of the interior. This technique worked well for Jupiter, whose tilted magnetic field produces a clear, consistent periodic signal. But Saturn's field is nearly perfectly aligned with the rotation axis, producing a signal that is far more subtle. And when scientists measured that signal, they got answers that seemed to change over time. Voyager 1 measured one period in 1980. Cassini measured a different one starting in 2004. The apparent rotation period seemed to be shifting by several minutes over the span of decades. This was physically impossible. A planet the mass of Saturn cannot speed up or slow down its rotation on time scales of years or decades. Something else was going on. In 2026, a team led by Professor Tom Stallard of Northumbria University published a study that solved the mystery. Using the James Webb Space Telescope, the team observed Saturn's northern auroral region continuously for an entire Saturnian day on November 29th, 2024. The instrument used was the near-infrared spectrograph, which measured the infrared glow of a molecule called the trihydrogen cation, a 3-atom ion made entirely of hydrogen that forms in Saturn's upper atmosphere and acts as a natural thermometer for the ionosphere. By mapping how bright and how hot this glow was across the entire polar region at once, the team produced the first high-resolution temperature and density map of Saturn's auroral zone ever created. What they found was that Saturn's aurora is not simply a passive display of light, produced by particles raining into the atmosphere from the magnetosphere, the way Earth's northern lights work. Saturn's aurora actively heats the upper atmosphere in an asymmetric pattern. That heating creates powerful winds. Those winds, flowing through the electrically conducting ionosphere, generate electrical currents, and those currents in turn feed energy back into the magnetosphere, sustaining the very aurora that produced them. It is a self-sustaining feedback loop, a planetary heat engine in which the aurora drives winds that drive currents that drive the aurora. This feedback loop creates a rotating pattern of atmospheric flow at Saturn's poles that circles the planet roughly once every 10.5 hours. But because the loop is self-sustaining and partly driven by its own internal dynamics, rather than being rigidly locked to the planet's rotation, its period drifts slightly over time. This drift is what had been fooling every previous measurement. Scientists were not measuring Saturn's rotation. They were measuring the rotation of an atmospheric engine powered by the aurora. And that engine does not spin at exactly the same rate as the planet beneath it. Saturn's true internal rotation period, determined by the Cassini grand finale gravity data and supported by ring seismology, is approximately 10 hours and 33 minutes. The apparent changes in rotation rate were never real. They were artifacts of a self-generating electromagnetic machine operating in Saturn's upper atmosphere. A machine so powerful that it deceived instruments across 4 decades of observation. Saturn's magnetosphere is not just a passive bubble around the planet, it is an active, driven environment. And one of the primary drivers of that environment is not Saturn itself, but one of its smallest moons. Enceladus is roughly 313 miles across. It would fit comfortably inside the borders of a small European country. By any visual standard, it is a minor body, an icy speck orbiting deep within the Saturn system, at a distance of roughly 148,000 miles from the planet's center. But Enceladus is one of the most geologically active objects in the entire solar system. and its influence on Saturn's magnetosphere is vastly out of proportion to its size. At Enceladus' south pole, a series of long parallel fractures in the icy crust, informally called tiger stripes, vent enormous plumes of water vapor, ice particles, and trace organic compounds into space. These geysers erupt continuously, fed by a subsurface ocean of liquid water that exists beneath an ice shell estimated at roughly 12 to 16 miles thick. The ocean is kept warm by tidal heating, the frictional energy generated as Saturn's gravity flexes and stretches the moon's interior on every orbit. Enceladus orbits inside Saturn's gravitational grip, locked into a resonance with the larger moon Dione that keeps its orbit slightly elliptical. And that slight ellipticity means the tidal forces vary throughout each orbit, rhythmically squeezing and releasing the moon's interior, and generating the heat that maintains the ocean in liquid form. The Cassini spacecraft flew through these plumes multiple times during the mission, passing as close as 15 miles above the surface on some encounters, and directly sampled their composition using its mass spectrometer and cosmic dust analyzer. The plumes contain water, sodium, and potassium salts, consistent with a salty ocean interacting with a rocky seafloor, silica nanoparticles that suggest hydrothermal activity at the bottom of the ocean, molecular hydrogen that could serve as an energy source for microbial life, carbon dioxide, and complex organic molecules, including some with molecular weights above 200 atomic mass units. This chemical inventory has made Enceladus one of the most compelling candidates for extraterrestrial life anywhere in the solar system. A 2025 study complicated that picture somewhat by showing that some organic compounds detected on Enceladus' surface might be produced by radiation from Saturn's magnetosphere rather than by biological or chemical processes in the ocean below. The question of whether Enceladus' chemistry reflects a living ocean or a radiated surface remains open, but the plumes do something else. The smaller ice particles in the plumes reach escape velocity and leave Enceladus entirely. They spread into orbit around Saturn, forming the vast, diffuse E-ring, which extends across hundreds of thousands of miles of orbital space. Meanwhile, the water molecules ejected by the plumes are exposed to Saturn's radiation environment. Ultraviolet photons and energetic particles strip electrons from the water molecules, ionizing them, converting neutral water vapor into electrically charged plasma. This plasma becomes trapped in Saturn's magnetic field and forms a dense torus of charged particles that encircles Saturn along Enceladus's orbital path. This plasma torus interacts with Saturn's rotating magnetic field, and the result, according to a major study published in February of 2026 by an international team led by Lena Hadid, is extraordinary. Enceladus functions as a planetary-scale electromagnetic wave generator. The interaction between the plasma from Enceladus's plumes and Saturn's sweeping magnetic field creates electromagnetic wave structures that travel along the magnetic field lines connecting Enceladus to Saturn's poles. These waves bounce back and forth between Saturn's ionosphere and the plasma torus around Enceladus's orbit, creating a crisscrossing lattice of reflected wave energy that extends over more than 500,000 kilometers from the moon. That distance is greater than the distance from the Earth to the moon. A body 313 miles across is reshaping the electromagnetic environment of a region of space larger than the Earth-Moon system. The Cassini data showed evidence of these electromagnetic connections not only during close flybys of Enceladus, but also along trajectories that passed far from the Moon, intersecting the magnetic field lines that Enceladus feeds energy into. On 36 separate occasions across 13 years of data, the instruments detected signatures of these wave structures, confirming that the connection between Enceladus and Saturn is not a local phenomenon limited to the Moon's immediate vicinity. It is a system-wide interaction that circulates energy and momentum across the entire inner magnetosphere. This means that when you look at Saturn's aurora from the outside, some of what you see is being powered, in part, by a tiny moon erupting water vapor from its south pole, hundreds of thousands of miles away. The geysers feed the E-ring. The E-ring feeds the plasma torus. The plasma torus generates electromagnetic waves. The waves travel to Saturn's poles and contribute to the auroral energy that drives the atmospheric heat engine discovered by the James Webb Space Telescope. Everything is connected. The moon, the ring, the magnetosphere, the aurora, the atmosphere. It is a single system, and the components are physically coupled through gravity, through magnetism, through the flow of material and energy across the vast distances between them. And Enceladus is only one moon. Saturn has 274 confirmed moons as of March 2025, more than any other planet in the solar system. They range from Titan, which is larger than the planet Mercury and has a dense nitrogen atmosphere with a surface pressure roughly 50% higher than Earth's, to tiny moonlets embedded within the rings themselves, some only a few hundred meters across. Between these extremes are dozens of mid-sized icy moons, each with its own orbital dynamics, its own surface characteristics, its own gravitational influence on the ring material and on each other. Titan deserves particular attention because it adds another layer of complexity to the Saturn system that has no parallel elsewhere. Titan is not just a large moon, it is a world. Its diameter of roughly 3,200 miles makes it the second largest moon in the solar system, after Jupiter's Ganymede. It is the only moon in the entire solar system with a substantial atmosphere. A thick blanket of nitrogen with traces of methane and other hydrocarbons that extends hundreds of miles above the surface and creates an opaque orange haze that completely conceals the surface from direct visual observation. The surface pressure on Titan is approximately 1.5 bars, about 50% higher than the atmospheric pressure at sea level on Earth. You would not need a pressure suit on Titan. You would need a breathing apparatus and extreme cold weather protection, because the surface temperature sits at approximately minus 179 degrees Celsius, roughly minus 290 degrees Fahrenheit. But the pressure itself would feel unremarkable to a human body. What makes Titan extraordinary, and what makes it relevant to the argument that the Saturn system is uniquely complex and dangerous, is its methane cycle. On Earth, water evaporates from the oceans, forms clouds, falls as rain, flows through rivers, and collects in lakes and seas. On Titan, methane plays the same role. Methane evaporates from the surface, rises into the thick atmosphere, forms clouds at high altitudes, and falls as methane rain. That rain carves river channels into the icy landscape, visible in Cassini's radar images as branching networks that look strikingly similar to river systems on Earth. The methane collects in low-lying basins near the poles, forming lakes and seas of liquid hydrocarbon, some of them comparable in size to the Great Lakes of North America. The largest, a sea called Kraken Mare, stretches roughly 620 miles across and contains more liquid hydrocarbon than all of Earth's proven oil and natural gas reserves combined. Titan has a weather system. It has erosion. It has shorelines. It has a liquid cycle that mirrors Earth's water cycle in structure, even though the chemistry is utterly alien. Cassini's radar instruments map these features across dozens of Titan flybys during the mission. And in January of 2005, early in Cassini's tenure at Saturn, the Huygens probe, built by the European Space Agency and carried to Saturn aboard Cassini, separated from the orbiter and descended through Titan's atmosphere on a parachute. The descent took roughly 2 hours and 27 minutes. During that time, Huygens measured the atmosphere's temperature, pressure, composition, and wind speeds at every altitude, painting the most detailed portrait of an alien atmosphere ever achieved. When it reached the surface, it landed on a frozen plain, scattered with rounded ice pebbles, smoothed by the flow of liquid methane in much the same way river pebbles on Earth are smoothed by flowing water. Huygens transmitted images and data from the surface for approximately 72 minutes before its batteries died. It remains the most distant landing ever achieved by a human-made spacecraft, and it confirmed that Titan is a world with active surface processes, a dynamic atmosphere, and a complexity that rivals anything in the inner solar system. Titan orbits within Saturn's magnetosphere, passing in and out of the magnetotail depending on the orientation of the magnetic field relative to the solar wind. Its thick atmosphere interacts with the magnetospheric plasma, stripping away atmospheric material and adding it to the complex chemical and physical environment around Saturn. Titan is not just orbiting Saturn, it is participating in the Saturn system the way a component participates in a machine. It exchanges material with the magnetosphere. Its gravity reshapes the orbits of smaller moons and influences the ring dynamics. It is a destination, a laboratory, and a complication all at once. The Saturn system, taken in its totality, is an environment of staggering complexity. Hundreds of moons, each one with its own orbit, its own gravitational influence, its own physical characteristics. A ring system spanning hundreds of thousands of miles, composed of trillions of particles in constant collision and constant erosion. A magnetosphere extending more than 1 million kilometers from the planet, filled with trapped radiation and shaped by forces generated deep inside the planet's metallic hydrogen interior. Electromagnetic wave structures connecting tiny moons to the planet's aurora across distances greater than the gap between Earth and our own moon. A self-sustaining atmospheric heat engine at the poles that fooled scientists for 40 years. Geysers feeding rings, feeding plasma, feeding the magnetosphere, feeding the aurora. Everything coupled, everything in motion, everything interacting across scales that range from microscopic ice grains in the rings to electromagnetic circuits stretching 500,000 kilometers through the vacuum of space. No other planetary system in our solar system has this level of interconnection. Jupiter is larger and more violently radiative, but its system is simpler. Saturn's system is a web, and every strand in that web is under tension. And in September of 2017, the Cassini spacecraft demonstrated what happens when something enters the system without protection. After 13 years of orbiting Saturn, Cassini's fuel was nearly exhausted. NASA faced a choice. They could let the spacecraft drift, uncontrolled, through the Saturn system, where it might eventually collide with Enceladus or Titan and contaminate those potentially life-bearing worlds with Earth microbes that might still be clinging to the spacecraft's surfaces. Or they could end the mission deliberately, sending Cassini into Saturn's atmosphere, where it would be destroyed completely, leaving no possibility of contamination. They chose destruction. On September 15th, 2017, Cassini fired its thrusters one final time to aim itself at Saturn. It entered the upper atmosphere at a speed of roughly 77,000 miles per hour. The first contact with atmospheric molecules created drag. The spacecraft's thrusters fired automatically, trying to keep the antenna pointed at Earth, trying to maintain the data link for as long as physically possible. For about a minute, they succeeded. Data flowed. Measurements of the atmosphere's composition were transmitted in real time, the final scientific observations of a mission that had transformed our understanding of Saturn. Then, the drag overwhelmed the thrusters. The spacecraft began to tumble. The antenna lost its lock on Earth. The signal, which had been traveling at the speed of light across roughly 900 million miles of space to reach the receiving dishes of NASA's Deep Space Network, went silent. Within seconds of losing orientation, temperatures on the spacecraft's surfaces soared beyond the melting points of its components. The structure broke apart. The instruments that had spent 13 years studying Saturn from the outside were now being consumed by the very atmosphere they had measured. Cassini melted, vaporized, and dispersed into the hydrogen and helium, becoming part of Saturn. The most sophisticated machine ever sent to the outer solar system was destroyed in roughly 60 seconds by the outermost edge of an atmosphere that extends tens of thousands of miles deeper below. That is what Saturn does to things that enter it. Not with malice, not with intent, just with physics. The atmosphere is denser than you expect. The pressure builds faster than you anticipate. The heat rises, the drag increases, and in less time than it takes to hear this, 13 years of exploration ended in fire and silence. And yet, from the outside, nothing about Saturn changed. The golden clouds did not ripple, the hexagon did not flicker. The rings continued their silent, grinding orbit. Saturn consumed Cassini the way it consumes everything that crosses into it, quietly, completely, and without any visible sign that anything happened at all. That silence, that total absorption of violence into calm, is not a side note. It is the core of the argument, and it is where we are going to end. Look at a photograph of Saturn. Any photograph. Pick the most famous one, the one Cassini took during one of its final orbits, with the planet silhouetted against the glow of its own rings, backlit by a sun that is almost 1 billion miles away. Look at the colour, that warm gold fading into cream. Look at the rings, impossibly thin and impossibly wide, curving away from the planet in a perfect, luminous arc. Look at the shadows the rings cast on the atmosphere below, and the gaps within them, dark and precise, like the spaces between notes in a piece of music. It is beautiful. There is no arguing with that. Saturn is, by almost any visual standard, the most beautiful planet in the solar system. It is photogenic in a way that no other world can match. Jupiter is dramatic but chaotic. Mars is stark. Venus is hidden. Neptune is a pale blue dot. Saturn is art. Saturn is the planet that makes people fall in love with astronomy. And now you know what is behind that image. Behind the gold is an atmosphere with no flaw, where winds exceed 1,100 miles per hour and periodic storms wrap the entire planet in turbulence. dredging material from 200 kilometers below the cloud deck and heating the stratosphere by 150 degrees Fahrenheit in a matter of weeks. Behind the rings is a debris field of trillions of ice fragments, orbiting at tens of thousands of miles per hour inside a zone of tidal destruction where gravity shreds anything large enough to hold itself together. Behind the calm exterior is a planet raining helium through its own metallic interior, generating enough heat to power atmospheric violence 4.5 billion years after its formation. Behind the silence is a magnetosphere driven partly by a 313-mile wide moon, whose water geysers create electromagnetic wave structures spanning more than 500,000 kilometers. Behind the Serenity is a planet that destroyed Cassini in less than 60 seconds and showed no visible sign that anything had happened. None of this is visible from the outside. None of it registers in the photographs that make Saturn famous. The storms hide beneath bland upper haze for decades at a time. The ring dynamics are invisible unless a spacecraft flies through them at close range. The atmospheric pressure, which climbs from 1 bar at the cloud tops to millions of bars at the metallic hydrogen layer, produces no visible signal at all. The helium rain that powers the entire system occurs thousands of miles below the visible surface, in conditions so extreme that no instrument has ever directly observed it. Saturn shows you beauty, and only beauty. Everything else you have to go looking for. And when you find it, what you find is a planet that is as physically hostile as anything in the solar system, wrapped in an exterior that communicates nothing but peace. In March of 2025, something happened that perfectly captured this duality. Saturn's rings appeared to vanish. From Earth's perspective, the angle between the two planets shifted until we were looking at Saturn's ring plane exactly edge on. The ring plane crossing occurred on March 23rd. The rings, which span roughly 175,000 miles in width, but are only about 30 feet thick in most places, became a razor-thin line that was effectively invisible through most telescopes. For a brief window, Saturn looked like a pale yellow sphere with no rings at all. Galileo experienced something similar in 1612, when the rings became edge-on during his early telescopic observations, and the strange appendages he had noticed 2 years earlier seemed to vanish entirely. He was baffled. He did not understand what he was looking at. We do understand now, and the understanding makes the moment more revealing, not less. It was a purely geometric effect. The rings didn't go anywhere. They were still there, still orbiting, still grinding, still raining material into the planet's atmosphere at hundreds of kilograms per second. The tidal forces within the Roche limit were still shredding. The particles were still colliding at full orbital velocity. The electromagnetic wave structures from Enceladus were still pulsing through the magnetosphere. Every process, every force, every mechanism of the Saturn system was still in full operation. But from our vantage point, roughly 850 million miles away, the most visible evidence of all that violence became invisible. Saturn looked bare. It looked ordinary. It looked like a planet with nothing to hide. And then, as Earth and Saturn continued along their respective orbits, and the viewing angle shifted, the rings reappeared. By November of 2025, they were visible again as a thin, delicate band. The beauty reassembled itself, and Saturn once again looked like the planet everyone loves. The jewel, the showpiece, the one that belongs on the poster. This is what Saturn does. It lets you see what it wants you to see. Not through intent, obviously. Saturn has no intent. It is a ball of hydrogen and helium with no consciousness and no agenda. But the physical result is the same. Saturn's appearance, from any distance at which a human being could observe it, is dominated by features that convey elegance, order, and calm. The violent interior is hidden beneath bland cloud layers. The ring dynamics are invisible unless you fly a spacecraft through them. The storms are suppressed for decades at a time between eruptions. The magnetosphere is invisible to the eye entirely. Everything dangerous about Saturn is beneath the surface, behind the facade, out of view. And the surface itself is one of the most visually appealing things in the natural universe. This is what makes Saturn different from Jupiter in a way that matters for the argument we are making tonight. Jupiter does not hide. Jupiter is exactly what it looks like. The atmosphere is a visible, roiling storm system. The great red spot sits on the surface, exposed. A wound you can see from 400 million miles away. The cloud bands tear and shear against each other in visible violence. Jupiter's radiation environment is the most intense in the solar system, and while radiation is invisible to the eye, Jupiter's general appearance communicates aggression. Everything about Jupiter says danger. When a spacecraft approaches Jupiter, the instruments start screaming long before the planet fills the field of view. The radiation readings spike, the particle counts climb. Jupiter announces itself the way a thunderstorm announces itself, with unmistakable force, long before it arrives overhead. Saturn is quieter. Saturn approaches differently. If you were aboard a spacecraft entering the Saturn system for the first time, the first thing you would notice is beauty. The rings would resolve from a thin line into a broad, luminous disk, growing more detailed with every passing day, the gaps and divisions revealing themselves one by one. The planet would grow from a golden point into a sphere of soft, warm color, its cloud bands appearing as subtle gradients rather than the sharp, aggressive stripes of Jupiter. The moons would appear one by one as faint points of light against the dark, each one moving on its own orbital track, each one caught in Saturn's gravitational embrace. The hexagon at the North Pole, if you were approaching from the right angle in the right season, would show itself as an elegant geometric pattern, strange and precise, and unlike anything else in the solar system. Everything you saw would be extraordinary. Nothing you saw would look violent. Nothing would scream danger the way Jupiter does from 500 million miles out. The instruments would be quieter. The radiation readings would be lower than what you measured passing through the inner Jovian system. Saturn would feel, to the human eye and to the human mind, interpreting what the instruments show, like a calmer place, a more orderly place, a place where things are arranged rather than thrown. And that feeling would be wrong, because then you would need to start navigating through it, and everything would change. You would need to avoid the ring plane, because crossing it means flying through a field of ice particles moving at orbital velocity, any one of which could damage or destroy your spacecraft on impact. You would need to manage your trajectory through the gravitational influence of dozens of moons, each one tugging you in a slightly different direction with every flyby. You would need to deal with a magnetosphere that, while less intense than Jupiter's, is still large enough and energetic enough to damage your electronics over time and to deliver cumulative radiation doses to any biological crew. You would need to keep your distance from the planet itself, because the atmosphere has no surface, no boundary, no safe altitude at which you can say with confidence, this is close enough. The closer you get, the denser the atmosphere becomes. And the transition from safe orbit to fatal atmospheric entry is not marked by any dramatic change in what you see. It happens gradually. The drag increases, the heating begins, and by the time your instruments tell you something is wrong, the timeline to destruction is measured in seconds, not minutes. Cassini crossed that threshold in its final seconds. The margin between orbiting safely and being destroyed was measured in minutes. The Saturn system does not feel dangerous the way the Jupiter system does, but it is dangerous. The physics is real. The forces are real. The ring material is real. The pressure is real. The only difference is that Saturn does not look like what it is. And that difference, for anything entering the system expecting the visual to match the physical, is the most dangerous thing of all. Because the instinct to lower your guard in a beautiful environment is one of the deepest instincts in any mind that navigates the world through vision. We trust beauty. We associate it with safety, with order, with benevolence. And Saturn exploits that association perfectly, not by design, but by physics. And we still do not fully understand the physics. This is a point worth sitting with as we approach the end. Saturn is not a planet that has been explained and catalogued and filed away. It is a planet that, even after 13 years of continuous close observation by one of the most sophisticated robotic explorers ever built, still holds fundamental mysteries. We do not know how old the rings are. The young ring hypothesis, supported by Cassini dust measurements published in 2023, places their age at a few 100 million years. But studies published in 2025 and 2026 have challenged the contamination model that underpins that estimate, arguing that the cleanliness of the rings may not function as a reliable clock if micrometeoroid material is being vaporized and removed rather than deposited. The question is unresolved. Whether the rings are as old as the solar system or younger than the first dinosaurs, we genuinely do not know. We do not fully understand Saturn's deep interior. The Cassini Grand Finale gravity data tells us there is a concentration of heavy elements at the center, roughly 12 to 20 Earth masses. Ring seismology, a technique that reads wave patterns in Saturn's C ring to probe the planet's internal density structure, tells us the core is diffuse, blurred, mixed into the surrounding metallic hydrogen across a region that may extend to half the planet's radius. But we have never directly measured any of this. We are inferring the interior of a planet from the wobble of its gravity and the ripples in its rings. It is extraordinary science. It is also incomplete science. There could be structures, layers, or processes inside Saturn that current models do not account for, because we have never been inside. We do not know why the hexagon exists with such geometric precision, or why it has persisted for over 4 decades without distortion or decay. The Rossby wave model provides a framework, a mathematical structure that explains how a rotating atmosphere can produce standing wave patterns with discrete numbers of sides. But reproducing the hexagon's exact behavior in simulations requires careful tuning of parameters, and the mechanism by which the hexagon remains locked to a fixed latitude, while the atmosphere around it flows at hundreds of miles per hour in different directions at different altitudes, is not completely accounted for. It is a feature that we can describe. We can photograph it, we can model it approximately, but we cannot say with full confidence that we know why it is there rather than not there, or why it has 6 sides rather than 5 or 7, or why it has survived this long when atmospheric dynamics should, by most intuitions, disrupt geometric patterns over time. We do not know whether Enceladus's ocean contains life. The chemical inventory measured by Cassini during its plume flybys, salts, silica nanoparticles, molecular hydrogen, carbon dioxide, complex organic molecules, is consistent with a habitable environment. The presence of molecular hydrogen in particular suggests active hydrothermal reactions at the ocean floor, the kind of chemistry that supports microbial life at hydrothermal vents in Earth's deep oceans. But a 2025 study showed that some of those organic molecules could be produced by radiation from Saturn's magnetosphere interacting with the icy surface rather than by chemistry or biology in the ocean below. The question of whether Enceladus's chemistry is biological, geological, or radiological remains entirely open. It may be one of the most important unanswered questions in all of planetary science, and it may not be answerable without sending another mission to fly through the plumes with instruments designed specifically to look for the molecular signatures of life. We do not know how much longer the rings will last. Estimates range from less than 100 million years to 300 million years, depending on which loss mechanisms dominate and whether current erosion rates are representative or anomalous. But the trajectory is clear. The rings are losing mass, they are eroding, and at some point in the future, they will be gone. Saturn will still be there. The atmosphere will still have no floor. The winds will still howl. The hexagon will presumably still spin at the North Pole. But the rings, the feature that defines Saturn in the human imagination, the thing that makes Saturn Saturn, will no longer exist. This means we are looking at Saturn during a specific and possibly brief chapter of its history. The rings may have formed a few 100 million years ago, or they may have been there since the beginning, but either way, they are not permanent. They are a phase, a temporary feature, a chapter that has a beginning and an end, and we happen to be alive during that chapter. Consider the scale of this coincidence. If the young ring hypothesis is correct, then for most of Saturn's 4.5 billion year history, the planet looked fundamentally different from how it looks now. It spent billions of years without its iconic rings, or with very different rings, before whatever cataclysmic event, a moon collision, a captured comet, a tidal disruption, created the current system. The rings that define Saturn in every photograph, every textbook, every child's drawing of the solar system, may be a feature that has existed for less than 2% of the planet's lifetime. We are not seeing Saturn as it always was. We are seeing Saturn during a narrow window when its violence happens to be dressed in beauty. And in a few 100 million years, the rings will be gone again, consumed by ring rain and micrometeoroid erosion and the slow, patient gravitational appetite of the planet they orbit. Future astronomers, if there are any, looking at Saturn from Earth or from wherever humanity might be at that point, will see a ringed planet that is losing its rings, growing thinner and fainter with each passing epoch. They might calculate when the rings will vanish entirely. They might study the remnants as the ring system fades to a thin, sparse band of dust, and eventually some generation will look at Saturn and see no rings at all, just a golden sphere with cloud bands and polar storms. Still dangerous, still bottomless, still raining helium through its metallic interior, but stripped of the feature that made it beautiful, the feature that made the danger invisible. There is something important in that image. A Saturn without rings would still be terrifying. It would still have winds faster than any planet except distant Neptune. It would still have the hexagon, that six-sided jet stream spinning endlessly at the North Pole with a cyclone at its center. It would still produce great white spots roughly every 30 Earth years, planet-encircling eruptions that dredge water ice from hundreds of kilometers deep and heat the stratosphere by dozens of degrees in a matter of weeks. It would still have 274 moons, including a world with methane seas and a moon with a subsurface ocean and geysers. It would still have a magnetosphere extending more than 1 million kilometers. It would still have a self-sustaining auroral heat engine at its poles that generates its own electromagnetic weather. It would still have no surface. It would still crush, dissolve, and absorb anything that entered its atmosphere, smoothly, continuously, without any warning or any flaw. All of that danger would remain, every bit of it, unchanged and undiminished. But without the rings, Saturn would also look dangerous. It would look like what it is: a gas giant. A massive, featureless ball of hydrogen floating in the outer solar system, intimidating by its size alone, no longer beautiful in the way it is now, no longer serene, no longer hiding. The rings are what make Saturn look safe. The rings are what transform a bottomless, storm-racked, pressurized sphere of metallic hydrogen into the jewel of the solar system. They are the feature that converts fear into admiration, hostility into elegance, chaos into apparent order. Remove the rings, and Saturn is revealed. It is still extreme. It is still hostile, but it is no longer deceptive. It no longer hides what it is behind a veil of geometry and light. And that brings us to the final point, the argument we set out to make at the beginning of this story. Saturn is not the most massive planet, that is Jupiter. It is not the planet with the most intense radiation. That is also Jupiter. It is not the planet with the fastest winds. That honor belongs to Neptune, whose wind speeds exceed Saturn's in certain measurements. It is not the planet with the hottest interior. Jupiter's core is hotter. By most individual metrics of planetary violence, Saturn does not hold the top position. Something else is always more extreme in at least one category. But Saturn holds a position that no other planet occupies. It is the most dangerous planet that does not look dangerous. It is the planet where the gap between appearance and reality is the widest, where the mismatch between what your eyes tell you and what the physics actually does is most extreme. It is the planet where beauty and brutality coexist most completely, not side by side, not in alternating layers, not in a balance that shifts depending on where you look, but fused together so thoroughly that the beauty is a direct product of the brutality. The rings are beautiful because they are a debris field shaped by tidal destruction. The atmosphere looks calm because the storms build silently for decades before erupting. The golden color is warm and inviting because ammonia ice crystals scatter sunlight in wavelengths that the human eye associates with warmth and comfort. Every visual quality that makes Saturn appealing is a consequence of the same physics that makes it hostile. Jupiter warns you, Mars warns you, Venus, shrouded in sulfuric acid under a crushing carbon dioxide atmosphere, warns you the moment you look at it with anything more than a naked eye. Even Uranus and Neptune, bland and distant as they appear, do not pretend to be welcoming. They look cold because they are cold. They look remote because they are remote. What you see is, in broad terms, what you get. Saturn is the exception. Saturn is the one planet that smiles while being impossible to survive. The planet that invites you closer while quietly hiding a gravitational kill zone, a bottomless atmosphere, a magnetosphere powered partly by the geysers of a tiny moon, and a self-sustaining electromagnetic engine at its poles that fool the best instruments in human science for 40 years. Saturn's danger is not loud. It is not obvious. It is not written on the surface. It is embedded in the structure, in the physics, in the elegant, quiet, ruthless mechanics of a system that operates at every scale, from microscopic ice grains to electromagnetic waves spanning 500,000 miles. That is why Saturn is the scariest planet, not because it is the most violent in any single measurement, but because it is the most deceptive. Because the violence is there, every bit as real as Jupiter's, every bit as fatal, and the planet's own appearance actively conceals it. Because the thing that makes Saturn the most admired planet in the solar system, its beauty, is the same thing that makes its danger invisible. The beauty is not a separate quality from the hostility. It is not a mask placed over the danger. It is the danger, expressed in a form that the human eye reads as safe. Saturn is not frightening despite its beauty. Saturn is frightening because of it. It is the planet that proves the most dangerous things in the universe are not always the ones that look the part. Sometimes, the most dangerous thing in the room is the one you would never think to be afraid of. The one that looks calm. The one that looks ordered. The one that looks like art. The one whose golden light and perfect rings and smooth, untroubled face have made you feel, from the very first moment you saw it, that everything is fine. Everything is not fine. Beneath those rings is a debris field born from the destruction of everything that got too close. Beneath that golden atmosphere is a descent without end, a pressure without ceiling, a heat that exceeds the surface of the sun that lights it. Beneath that calm is a planet that radiates more energy than it receives, powered by the rain of its own internal chemistry falling through a sea of liquid metal. Beneath that silence is a system of moons and rings and magnetism so interconnected that a body 313 miles wide can reshape the electromagnetic environment across a distance greater than the span between the Earth and its own moon. Saturn is the scariest planet in the solar system. And it is not even close. Not because nothing else is dangerous, but because nothing else is this good at hiding it. Look at Saturn tonight, if it is visible in your sky. Look at the golden light. Look at the rings. If the angle is right, that thin bright line or that wide luminous disk, depending on where we are in Saturn's long, slow tilt cycle. Appreciate the beauty. It is real. It is one of the most genuinely beautiful things in the natural universe, and no amount of understanding what lies behind it should take that away. But remember what you now know is behind it. The storms building silently in the deep atmosphere. The pressure climbing without ceiling through layers of gas that become liquid, that become metal. The kill zone where moons are torn apart and their remains grind forever in orbit. The debris raining into the atmosphere at hundreds of kilograms per second. The liquid metallic hydrogen generating a magnetic field that reaches millions of miles into space. The helium rain falling through that metallic sea, releasing the heat that powers the whole machine. The electromagnetic engine at the poles, sustaining itself through its own feedback. The moons feeding rings, feeding plasma, feeding the aurora, feeding the winds. The planet that consumed Cassini without a ripple on its golden face. Saturn is beautiful. Saturn is terrifying. And the reason it is both, at the same time, without contradiction, is the thing that should keep you thinking about it long after tonight is over. The beauty is not a disguise placed over the danger. The beauty is the danger, rendered in a form the human eye reads as safe. And that is why, of all the planets in this solar system, Saturn may be the one that deserves your respect the most. Not because it is the largest, not because it is the most violent, but because it is the one most capable of making you forget what it really is. Good night.